So hi everyone. Today we'll have a fun demo-filled session with a bunch of tools that sometimes might be useful to you, and see three things in the process: some of the science part, some of the process part, and some of the people part. And just have fun at the end of the day. So before I explain the details, I want to actually explain the problem that we are going to solve in the next 40 minutes-ish. And it's the problem of search. So this is kind of motivated by the problem we have all faced as kids, where we are trying to play the game of Where's Waldo? And we have this small, tiny character in this gigantic canvas that we are trying to find. So can we do that? And that's kind of a problem which is very similar to remote sensing and Earth observation. We have this gigantic world, like on NASA Worldview search, with 175 square miles of area, 365 days a year, and 20 years of data. And we are trying to find examples that a curated set of all potential examples of a particular kind, so you can start your research. In this example, if you're trying to find wildfires, for example, you can go there, take a selfie of that wildfire, then move to the next place and keep moving till you find another example and be an expert enough to know that this is a cloud or this is a wildfire. So in this example, as the video was playing, there were two examples that we have taken a photo of. Maybe we might get lucky on a third one, but that's the point. You have to carefully, painfully go through this map of the world, trying to look for these patterns. And when you look at the scale of the data over 20 years, that's humongous. Currently, NASA says they have about close to 40 petabytes of data of this kind, and it's going to explode to 250 petabytes in the coming 5 years, and that's just humongous. So the task for today is, can we find examples of satellite images that you are interested in? That's the key task, but over the last 20 years. And it's like finding a needle in a haystack. It could be related to even searching for a particular galaxy or a celestial object. So either we can do it painfully or we can automate this process in some way. Now, if somebody is working in the field of deep learning, they will say, this is like one of the most basic problems in deep learning, because similarity search is a known thing. You convert an image or whatever your data is to a meaningful representation by training a network, and then try to find other things which are similar to it. And this is a known thing. Takes maybe 10 to 20 lines of code to do that, not hard. Now, the problem is, first of all, this is ultra large scale data. That makes this problem tough enough for the scale you are dealing with. So how do you scale it? That's one. The biggest problem is that we don't even have any labels to start with. So if your data is totally unlabeled, what will you train your supervised network on? That's a fail. Thirdly, there is multiple concepts happening in the same image or data that you're seeing it. So in one image, you could have a hurricane, a desert, and an ocean, all three within the same image. So those multiple concepts make it also harder. And finally, the data is severely imbalanced. Your chances of having a hurricane might be 0.0001, whereas the chance for this to be water is 70%. And imbalance is like an evil to machine learning. Networks don't train. So we have a bunch of things to solve in here. So instead of me showing you all the work and then at the end showing the demo, why don't we just cut to the chase and actually have a demo running? So in this particular example, let's say we are trying to look at these fluffy clouds. By the way, I'm not a scientist, so I know little about this area, but I know something is working here. in this particular example, you search for a particular pattern and you are getting images which are near similar. So maybe you wanted something slightly more structurally different, dense clouds on one side and more fluffier on the other side. And you can see these examples are coming back. That sounds close enough. All right, maybe you have been in this pandemic world and haven't taken a vacation in the last 2 years. So let's try to find some vacation spots maybe. Oh, all right, this looks like a nifty place. Let's search for something similar, and hopefully it gives you better ideas of places to go to. And yeah, it's giving you, those green and blue spots, coral reefs, and the kind you would have wanted. Now, the key thing in here as you watch the demo is it's large scale data, that's fine, but there is not a single labeled example that it was trained on. Another example here, and this is like something that is really interesting. So, places where the evergreen chip blocks your entire canal, if you search for that, you get this ocean, land sandwich, and even better, a desert, ocean, desert sandwich. Now, think about this carefully. If you're trying to train a classical classifier where you give it an image and say, hey, this is a desert or this is an ocean, it would not have been able to understand the structure, whereas this example without any labels was unable to understand the particular structure you were interested in. And that's pretty impressive. And let's see how this was all done with self-supervised learning. So, traditionally, if you had to train a classifier, you have an image on one side and you get the labels. In this example, it's ocean, coastal fog, and forest, all that represent the particular image. But we don't have that. So here's an idea. What if you take that image on the left-hand side and augment it? So let's say we rotate it by anywhere between 0 to 360 degrees. How about we crop that image to some slight dimensions? How about we change the color and contrast slightly a little bit? And if we combine all of these, we can get a new image. The point to notice is that the image on the left is the same image on the right with just a few augmentations. And to a human like us, it's the same image at the end of the day. Could we let an AI network essentially learn the fact that the left and the right is exactly the same thing, figure out why? And behind the scenes, it basically builds the understanding of why this and this is very similar. And with that, we get this similarity metric out of it. So this was a paper from Google in 2020 called SimCLR, which showcases, we take one example on the left-hand side, let's say this hurricane, one example, and come up with two augmentations. And we come up with an example of a desert and an ocean. We come up with two augmentations of it, and let the network learn that for some reason, the two augmentations on the left-hand side are similar, the two augmentations on the right-hand are similar, but they overall are just dissimilar. Similar things will attract, dissimilar things will repel, and that's how you get this measure of similarity. And as you might guess, features like the colors, the structure, they play a lot of role. So all the playing behind the scenes come up with the kind of augmentations that we can build. So that's the theory, but we don't like theory, we like applications. And that's from which we get the Worldview search application, which the SpaceML team has been building for NASA, NASA impact team for specifically. So as I show you the pipeline, the key things that, there'll be a lot of details, but the things that you might want to know at the back of your mind are that the aim here is to reduce the barrier for a new person to enter this field with the least amount of programming required or AI knowledge required. So most of the tools are built in the way of like a one-liner tool, so it can be run easily without knowing behind the scenes the advances in, self-supervised learning or anything. It's also built for cost effectiveness. So it's running with the maximum hardware performance one can achieve whether you have a supercomputer or whether you have your own personal laptop. And then finally, they are built modularly open source so that we can have high quality software which is updatable, upgradable over time, and more contributors can join. So just keep that in the back of your mind, all right? So if you're building an entire pipeline from start to end, it always starts with downloading the data. And that's from NASA Gibbs. But if you're downloading data yourself from this, you have to know what API means, how to write a program which can go through download data. And if there's an error, what to do, how to retry. That's a bunch of work. And even worse, if you actually are not you're not traditionally in the field of satellite imagery. So for that, we built Gibbs Downloader. Gibbs Downloader is this one-line command you write to download any of the 900 products on NASA Gibbs and make it as easy as possible. How do you use it? You simply write GDL, write the start and end date, write the bottom and upper coordinates, and you start getting your data downloaded. Even more interesting is that you can download data in different formats, obviously like images, but if you're going to use it for AI training eventually, you can process the data to be more efficient and higher performance for AI training, like TensorFlow record format. So it does that behind the scenes too, and there are like many parameters that you can add. But you can also do fun things like make animated versions. You had people who use this to make TikTok videos and educate their fellow teenagers. So that's kind of nice. Simply add a parameter. But even more interesting is that what if you actually did not even know the product you want to download and you want to search? You can go to NASA's website and browse through 900 products, or you can use it and simply write what you are interested in. Maybe you are interested in infrared, and it gives you back the particular imagery, right? It's kind of like the Google for NASA Gibbs at the end. So give that a try. It's your life easy. All right. So if you've downloaded the data, what next could you do? You want to train a network using self-supervision training. So let's do that. This is Self-Supervised Trainer. It's literally a single line of command, Python train.py, and then you enter your folder where you have all your images, and it does the job for you. Literally, give it the path, it trains a network in the next few minutes to hours. And even better, if you happen to eventually have labeled data, like some amount of labeled data, you can run the second command to train a supervised classifier. The key point here is if you run the first command and then on a smaller amount of data run the second command, you need very few examples to have a fully trained convolutional neural network. Again, one of the themes, only on the command line, modular and highly scalable. And if you happen to have more budget and have multiple nodes with multiple GPUs, it takes care of it behind the scenes. So that's nice. So here's an example. We dumped a single day of satellite imagery from VIIRS dataset. And if you look at this and make a TSNE cluster, it kind of makes some sense. The oceanicness or like the wetness increases as you go north. It gets drier usually as you go south. And similarly, you have deserts on the left-hand side and pure clouds on the right-hand side. So it's making some sense, if you watch it in a very peripheric manner. But if you go slightly deeper into it, you can see like the patterns of clouds that start emerging in. Here's another example where the same thing was done, except with the clouds removed. And then you can see more higher grained details. So as a practitioner, it's up to you on what kind of pre-processing you do to the data. Put that data in a folder and run the command, and it does the rest for you. And then here's another example where somebody who's just interested in the clouds and not on the the land and ocean features, they took the data and it started building some patterns of the clouds. All right, that's nice. But maybe you can go a level deeper interactively. So this was a work done with the Space Telescope Institute, where they were looking at astronomical objects, and we repurposed this code for satellite data sets, where you can actually move your mouse over these particular clusters, and it will show you for the particular thing you click, the nearest items interactively. Really helpful to understand, what your model, is it even working or not. Very neat. So to put this thing a little bit in perspective, I am going to bring Abby to ask her a question. Are these the same image categories?
Just by human eye, I would probably say yes.
Exactly, I did that too, but they are not. They are totally two different classes in the RESIS data set. Small residential, medium residential, okay? But you're not done yet. Now again, are these the same image categories?
I would probably also say yes.
Yeah, this time you're right. But if you visually look at it, they are actually different looking, right? We know that because it's a basketball court. Similarly, these two.
Ooh, I would say yes again.
Exactly, that doesn't happen. I mean, that's why we're playing the game, so that what we expect is not the answer. All right, thank you for volunteering here. And that's the point. The data sets like RESIS 45, it's about 30,000 images, 45 categories. They are hard. And even on these data sets, it's doing pretty amazingly. We're up to about 100 neighbors. It's able to understand the same class with close to over 50% accuracy. So what that means is, given an image, if you find the 100 nearest neighbors, or at least at like rank 20, if you find at rank 100, if you get the 100 nearest neighbors, it's still able to get half the times items of the same class that the scientist was interested in. So the point I'm getting at is, instead of like manually going over your data set, you could take one image and then spend about double the effort to the number of images that you had to collect on this particular data set. And that's pretty promising. All right. I want to also, put this in perspective that when we started with, we could barely get to rank to like 15% accuracy at rank 10 when we started this problem. And in about, a year, we're able to get it to much higher numbers on a hard problem. So two different researchers, over time, I think things become better. The other thing I'm really proud here is the tool set, as you can see here, is built for maximum GPU utilization. Usually, you need to be a practitioner with deep knowledge on scalability to know how to maximize the GPU utilization. Maybe, you don't have those resources and you are a student and you have free collab notebooks on what Google gives you, and that's the max you can maximize. So instead of knowing the details, it just does it for you behind the scenes. So that's pretty neat. All right. So now that you have downloaded the data and you have trained a model, now starts the fun part, which is actually now serving it and being able to show you the nearest examples. And that's we go towards the cloud side. So first we take all these images and we basically store this model in a model store. Then we take all the images that you had in the folder and generate embeddings out of this model that you trained. So now we have those meaningful representations in this embedding store. And now what we need to do is build an API where we can take an image from the user and then find those nearest meaningful embeddings, essentially, and give it back to the user. So that's what our aim is. So for that, I'm not going to go too much in detail, but at the high level, we built a scalable indexing and search API. We went through over 30 tricks to make it fast and scalable, but still cost efficient. So to make things fast, given the amount of data that one would have, parallelizing downloads, using approximate nearest neighbor libraries for sub-second million scale, partitioning the data, and I'm going to show you a couple of examples. So one thing that you always do is, you beg, borrow, steal, and you try to find things that somebody already has done, so you don't have to do it yourself. So there is this fascinating area of approximate nearest neighbor search. What it essentially does is it approximates with some level of accuracy loss to be able to find items which are similar, but at much higher speed. And there's a website, it's called annbenchmarks.com, and you can go there and try to find who would be better as of today. And we found if you do it yourself, like in Python or using scikit-learn, it usually gives you like a really low speed. You see that red button at the bottom. And we selected libraries like Scan, which are more recent, and they give you close to 5,000 queries per second when you're searching. As it so happened, you find bugs also as you do things. Things are not as nice as you expect in research papers. So we ended up with a library called Face from Facebook. And the cool thing about this library is that it does pretty decent when you have to do nearest neighbor search. But if you happen to have GPUs, it just speeds up 4x. So Facebook uses it for its images behind the scenes, and that's been quite useful for us. The second thing we learned is that when a user comes in, you can index the data based on, so you have all this data, right? Like over 20 years, and you want to break it down into chunks so that you don't have like one gigantic index. You have these smaller indexes. So you can divide this data by dates, by resolutions, like the spatial resolution, and by the layers. So maybe you are looking for modus or you are looking for weirs. So you can divide and conquer here. And why that's important is that now if a researcher comes in and says, hey, I want to search on a range from August 17 to August 19, 2020 for 512 into 512 resolution, 512 kilometer into 512 kilometer resolution, we can pinpoint a set of smaller indexes and reply back. And we can basically be faster at this. And this makes things a lot more parallelizable, which is the second word to say for cost effectiveness. We can also keep things in like cold storage and bring them up based on the researcher's needs. So that also makes things more cost effective. Awesome. So now that we have done the whole journey of the backend infrastructure and the training, now we can get to the fun part, which is, I apologize, I see everything is fun because it honestly is. So you luckily saw this part already at this end. So we are trying to convince NASA that, hey, you should change your Worldview search application. And you can imagine how many steps and processes that would take. A quicker way was, hey, let's take the NASA Worldview website and build a Chrome extension which just changes the code on top of it. So now a researcher would go download this Chrome extension, and this just works on top. And that's like one way to prove the concept works, go to some level of testing and implementation, and then eventually be able to bring that code into the main website. All right. Now, this was nice. So you understood the whole journey of taking one image and then coming back with maybe 50 to 100 images which are similar. All neat. But at the end, the whole reason we are doing this was because somebody wants to start a scientific study and they want to have a curated set of data, essentially. And this curated set of data, you want to be exhaustive. You don't want to miss out. So we need to get there before we start the study. What that means is you need to label data. So we said, let's label data. And how do you label data? Well, how about swiping right or swiping left? So we call it Tinder for NASA. So essentially, you put your unlabeled data set in a folder and start swiping left or right. And as you do that, the data just starts, you can see on the left-hand side, the folders, the data is just propagating into label positive, label negative. Straightforward, right? Now, this gets even more fun because you as a researcher can dump all your data in a folder. And then it will give you a shareable link. And you can share this link to all your friends. And they can start labeling too in a crowdsourced way. And the best part is that you don't need to know infrastructure or networking or firewalls or anything, because it literally is running from your own laptop. You don't need to do much. We have taken care of the things behind the scenes. We did a test demo and we were able to label 500 images in like a real call in 73 seconds, because we got a bunch of people together. Like I think there was like maybe some 20 plus people labeling data all together. And when they see examples, people just get fast. Oh, it also does some level of competitiveness, like a game on like how many seconds it's taking you to label, so people get fast. And in case they make a mistake, they have an option to fix it. So easy. Alrighty, so now that we know how to label data, that should be the end. But we want to go a little bit further. So now we realize that we can get to quite a level with this, self-supervised training and labeling, and that's good and all. But we have a gigantic data set in petabytes. Wouldn't it be better if we could get an AI model to actually go over this entire data set? Because similarity search is, has its limited amount of accuracy that it can go on a real world data set, especially with all the, examples I was showing about why it's hard. But if we can get an AI model to do that and have some way where we have a human in the loop, so the human teaches the AI the kind of examples to find, the AI model makes guesses, some of them will be incorrect, and then shows some of the harder examples to humans. And then we do that in a loop. That way we can get the AI model to get to a level where it's smart enough to now be confident and go over the entire data set. So could we do that? So that's what we're about to do. So depending on maybe more the data set you have, an classifier would do a better job, and that's what we want, a classifier now. So what we are going to do is the world of active learning. Essentially show it a few examples and train it. So let me show you what we do. We take a few examples as a seed data set, train a model, and then do a forward pass over the entire unlabeled images. And when the supervised model does that forward pass, it's trying to find things it's, uncertain about. It will select some of those uncertain images, the most confusing images, and show it to a human oracle, which is you. You will say, you know what, yeah, these 20 images, this is the positive, this is the negative. So now you have those, let's say you started with 100 images, you got a 60% F1 score, then you label the data set, select label data sets, and it gives you 100 more examples. Now you have 200 data points. You'll have a better model, and this loop goes. After showing another 100 examples to humans, you have 300, and the F1 score keeps getting higher and higher. And you reach a point when you are like, okay, now let me take the entire, the confident model over the entire data set. So that's the whole theory. And there are many ways of doing active learning. The simplest way is just finding things for a binary classifier, which are at 0.5 probability, because 0.5 on a scale of 0 to 1 means utterly confusing. That's the simplest way, and we have better ways. Now, this is nice. And this is what's written in books. In theory, it's known. The problem is that when you go on a data set with 10 billion images, a single forward pass from a convolution network takes $30,000 and 21,000 hours to complete. That's just a crazy big number, right? And you'd probably have to do 10 passes over this data set. That's $300,000. I mean, we can get maybe 2 researchers in that amount than like just trying to do forward passes. That's kind of expensive. So we did a few tricks. The first thing we did was that here's an idea. You can generate a representative sample of all those embeddings. And if you take equidistant embeddings, it's kind of like getting a diverse buffet of every potential kind of images. So your big data sets, you basically select a 100,000 representative sample. That takes like 13 minutes to do a forward pass. So what you do is you essentially have a search engine behind the scenes on that billion scale, and then have a smaller 100K example data set on which you do the forward pass. You find your confusing examples on this 100K example, and you find those examples, you label them. You then ask your bigger search engine, could you give me 100 examples very similar to the most confusing examples I had? What's really happening is that you are now getting access to billions at the cost of pennies, because you do your forward passes on 100K, but you get access to the most confusing from those billion scale. And that has been like really helpful in reducing the cost and speed. So the biggest label data set that we could find is the RESIS 45 data set. And one example just to showcase here is on 27,000 images, if you had to take a human to label it, it would have taken 38 hours. Whereas if we use the active learning system, we are able to curate about 82% of the images the researcher was interested in, starting from one image in just 2.9 hours. And this looks like a pretty neat image number. Let me show you a better example. So another example was we took this image of an island and then tried to find all other islands from 5 million potential tiled images. And we are able to identify 1,000 islands starting with that single image in just 52 minutes. Now, to put this in perspective, this would have taken somewhere around $105,000. We kind of were able to do it for almost free. So that's the point of being able to curate data sets with the limited resources you have. Necessity is the mother of invention, and that makes things possible. So that's cool. And that's pretty much how you go from a single image that you're interested in searching and taking all the way through to make a catalog quality data set. I should mention that while we are building it, we made two versions. One of them is something that you can run on your laptop up to about 5 million images and do the searching and all. And if you want to go beyond 5 million, you need to know cloud. And that's where some of slightly more intricate knowledge comes in. So we have some templates on how to take it to the cloud. The nice thing is NASA is currently building that system where any researcher with any need could come in and search on that petabyte scale. So that's kind of, you have some bigger resources coming up in future. So that's nice. Other additional tools, as I would mention that most of the people who participated in this had no idea about earth science. And so we had slightly fresh perspective, and then we just had to figure out how to solve it. So as an example, oh, I gave you the answer already. Okay, it's time for Abby to come to the quiz 2 of the day. All right, anything funky you see in these images?
Well, I think one of them has planes. So I would say that one looks quite funky compared to the rest of them.
All right. So the answer actually is that this was the original image. And we had to build a system to fill in, these things. And you notice that it's kind of pretty hard to know even for humans, right? That something was funky in here because we started with this image. The reason why we had to do that was because if you take some of the older Modis imagery, you have these gigantic empty spots. And these empty spots, if you train a self-supervised network, it thinks that these black spots are actually a very important structure. So it will start giving you more black empty items, which you are not interested in. And so we just built a system to fill in. We tried GANs, and then we tried a system to randomly take pixels weighted by the distance near the black empty spot and fill it. And it does a pretty neat job. And we are able to, essentially it was trying to fool the AI network, to not be able to see any pattern. So when it doesn't see any pattern, it just thinks it's like random noise and it just picks the important stuff. And that's nice. Cool. Another example that was really impressive was we have this, so essentially the data set that you see for Earth is a big canvas, and you can divide it into smaller size tiles. And when you do this whole image search, like you see on the left-hand side, there's a horse that is doing, let's say it's doing a jump, but I think there's a better word for this motion. It's not a jump, right? If you try to find similar images to that, the normal network, like an ImageNet network, will pick, oh, the grass and sky is the concept, and that's why it's giving you, a dog with a frisbee, a horse on a green field, and then, two more images on a green field. So I think green field is something it's capturing a lot more. So we tried to take it through a multi-resolution pipeline where it gives you a score based on smaller level matches and bigger level matches and similarity. Kind of like how you would imagine, let's say Google Images to go from an image from start to end. And when we did that, it was pretty impressive. This image on the left, leave the first rank image because it's supposed to be that, but rank 2, rank 3, rank 4 are all horses, all grassy fields. There's an audience, and that you can see there's like a impressive improvement. But here's the really impressive part, which we didn't start with an aim, but got to. If you see, there are 2 giraffes, and the giraffes have their neck intertwined. The bottom ImageNet network will just figure out, oh, this is a giraffe, and this is on a grass, and that's what it's giving you. But on the top, it's giving you 2 giraffes in every example, and in some examples with their necks intertwined. By the way, the model in the bottom and the top is exactly the same model at the top and bottom. It's basic ImageNet. So the TLDR is our network started to count based on trying to do multi-resolution search. Another thing, which is the necessity is the mother of invention. When you take an imbalanced data set, training a network is very hard. So here's an example. We took A, B, C, D, E, and F, and we gave 200 examples, 400 examples, 800 examples, to all the way to 6,400 examples, right? So it's 1:64 imbalance ratio at the end, and trained a supervised model. Supervised model, this is as good as life gets. We could barely get any accuracy. So you'll see the F1 score class-wise, and you'll see that E and F got like good classes, F1 scores, but A, B, C, and D could barely get. And then we tried to use our diversity logic that I was talking about earlier to sample the data, sample equidistant embeddings in this 3-dimensional or n-dimensional space, and then use it for training. And we're able to get like a pretty good metric. So we're able to get 34% before and 89% F1 score afterwards. And this is because the samples that we did for the training data, as you can see on the right-hand side, they were kind of better balanced than the left-hand side. We divided our teams into focusing on these smaller individual problems, and then everybody was fighting to make each part happen, and then we just joined them together in that bigger pipeline. Awesome. Finally, as I'm like approaching the end of my presentation, there's also, turns out there are cross-domain applications. So Rick White and Joshua Peak from the Space Telescope Institute, they use the Hubble image similarity dataset, which is from Hubble Space Telescope. And here's the example image, which kind of makes sense, where the nebula and the celestial patterns of a particular kind of make some sort of a pattern. So that was neat. Jeffrey Smith from SETI Institute took images from Voyager and Europa missions and was able to build these clusters. The most impressive part is they just saw the presentation like you are seeing right now, and in the evening wrote that one-line command, and in the morning sent me these images. Point being, this could just lead to another grant that you want to file for. It's a one-line command, so why don't you try it on your data sets? That's the TLDR. I recently found that I was at an event, I was giving my presentation, and then right before my presentation, somebody came in who was already using this, and they were using it on a space biology data set. So, it's built for like whatever need you'd have, as long as right now it's in 3 dimensions. So it's 3 channels like R, G, and B images that we're using, but it could be, any 2D matrix with 3 numbers. So that's 3D matrix that you could use this for. And yeah, NASA, several teams at NASA are also using it, so that's cool. Okay, I kept blabbing for 44 minutes, so I should probably introduce our team. So you might know about Frontier Development Labs, which is this summer AI accelerator for NASA and UK Space Agency. By the way, it's most of the people who join in are PhD, postdoc, lecturers, and there are like teams of 4 where there are 2 AI specialty and 2 science specialty. They make a team of 4 people to solve for moonshot problems. They have been getting some really great results, but usually the people that end up, after all the interviews and all, have like, this kind of a makeup of PhD, postdoc, and few incredible masters, right? All the work that you actually saw was actually done by high schoolers and undergraduates. That's the difference. We felt that we can open the opportunity to citizen scientists who might not have it, give them the mentorship to take it to the end and get high visibility at places that they would not assume with their background. And that was a pretty incredible part. We have people from Mexico, South Korea, India, US, Singapore, Germany. We had one person from Nigeria who would go to a cyber cafe to join for calls because the person didn't know if they will have electricity at home, right? And someone from Frontier Development Labs, James Park, paid for his internet bills to be able to join for these calls. That's a pretty impressive human story. We had 2 people who were English teachers and they changed their career, learned programming, and actually got data scientist jobs. One of them actually now teaches data science. One of them is a director now at a data science education company. So it's pretty impressive human side story. So SpaceML, which is essentially this part which goes towards the citizen science side, we essentially try to make these tools which can become self-service, high-quality tools, put them on GitHub, put the models and data and make them available, and also, showcase how this can be done with MLOps to put them in production. So you can look at SpaceML projects on spaceml.org, which is basically this accelerator for NASA. Finally, we need to end things on a fun note. And that's where, I have to end on the fun note. Essentially, this is our team. So I'm going to stop the call now and open to questions.